Hey there, welcome back to the Sleepy Professor. I'm so glad you're here tonight. You know right now, as you're settling into bed, maybe adjusting your pillow just right, pulling that blanket up to your chin, there's something extraordinary happening above you, something so vast, so quietly magnificent, that most of us never really stop to think about it. And tonight, we're going to think about it together. Gently, slowly. No rush at all. We're going on a journey, not anywhere loud or chaotic, but upward, past the ceiling of your room, through the whisper-thin atmosphere, and into a darkness that's anything but empty. We're exploring one of the most beautiful questions a human mind can ask. How many galaxies exist in our universe? Now, I know that sounds like a simple question, almost innocent, really. The kind of thing a child might ask while lying in the grass on a summer night. But here's the thing. It's one of the most profound questions we've ever dared to wonder about. Because to even ask it is to acknowledge the scale of everything. To admit softly and humbly that we're very small but endlessly curious. So get comfortable. Let your shoulders relax. Let your breathing slow down naturally. You don't need to remember every single detail I'm about to share. Just let the ideas wash over you, like gentle waves on a quiet shore. Close your eyes if you want, or keep them half open, whatever feels right. Let's drift together into the cosmic deep. The sky above us, a window to forever. For most of human history, we thought the Milky Way was everything. Can you imagine that? Thinking that the glowing band of light stretching across the night sky, that misty ribbon you can see on really dark nights, was the entire universe. When ancient people looked up at that glow, they told stories. The Greeks thought it was milk spilled by the goddess Hera while nursing the infant Hercules. The Romans called it the pathway of the gods, a celestial road where divine beings travelled. In China, they saw a river of silver light flowing through the heavens. The Maya believed it was the backbone of the sky itself, holding everything together. And you know what? None of these interpretations were wrong. They were human attempts to describe something larger than comprehension, something that made them feel small and connected all at once. But here's what they didn't know, what they couldn't have known, is that every single star they could see with their eyes, every tiny point of light, belonged to one massive structure, one galaxy. Think about that for a second. We live inside a galaxy. It's like living inside a cloud and trying to figure out what the cloud looks like from the outside. For thousands of years, we had no idea we were even in something. The night sky we see, as grand and overwhelming as it seems, is actually just a local view, like standing in a forest and only seeing the trees immediately around you, not realizing the forest stretches for hundreds of miles in every direction. Before telescopes existed, before anyone could magnify the heavens and see deeper into space, the Milky Way represented the boundaries of human understanding. It was our cosmic home, and it seemed vast enough, infinite even. The stars were markers of time, navigation tools for travelers crossing deserts and oceans. They were the backdrop for mythology, the canvas on which humans painted their gods and heroes. Every culture looked up and saw patterns: Orion the Hunter, Ursa Major, the Great Bear, the Southern Cross. These constellations weren't just pretty pictures, they were practical. They told farmers when to plant. They guided sailors home. They marked the passage of seasons, and marked the passage of seasons. But what people didn't realize, what took thousands of years to discover, was that those familiar patterns were just the nearest stars, the closest neighbors in an incomprehensibly larger structure. The faint, ghostly glow of the Milky Way itself, that band of light you can see on dark nights away from city lights, that was actually our view from inside the galaxy. We were looking through the densest part of it, seeing billions of distant stars all blurred together into one continuous stream of light. The first glimpse beyond. everything started to change in 1609. That's when Galileo Galilei, this curious Italian astronomer with homemade telescopes, pointed one of his instruments at the Milky Way, and what he saw shocked him. The smooth, glowing band wasn't smooth at all. Through his telescope, it broke apart into countless tiny points of light, thousands upon thousands of them, more than anyone had imagined. The Milky Way wasn't a mist or a cloud or spilled milk from the gods. It was stars, individual stars, billions and billions of them, so numerous and so distant that our eyes couldn't separate them. They all blended together into one continuous glow. That moment, that simple observation, was one of the first cracks in the wall of our understanding. Suddenly the universe expanded. What looked like fog was revealed to be depth. What seemed simple became incredibly complex. The sky was no longer a flat ceiling decorated with lights. It was a vast layered structure, stretching farther than anyone had dared to imagine. And that was just the beginning. Over the next few centuries, astronomers built better telescopes, bigger lenses, more sensitive instruments, and with each improvement, they saw deeper and found more. William Herschel and his sister Caroline spent years systematically mapping the stars, counting them, measuring their brightness, trying to understand the shape of our cosmic home. Herschel imagined the Milky Way as a great disk of stars, with the sun somewhere near the center. He wasn't quite right about our position. We're actually off to one side, but his intuition was extraordinary for his time. He understood that the stars weren't scattered randomly through space. They were organized, structured, part of something much larger than individual points of light. The idea that we lived inside a galaxy, inside a massive organized collection of stars, began to take hold, even if the word galaxy didn't quite mean what it means today. Our galactic home, the Milky Way. Let's talk about where you live, not your city or your country, but your cosmic address. The Milky Way is a barred spiral galaxy. Now, I know that sounds technical, but just picture this with me for a moment. Imagine a giant cosmic pinwheel slowly spinning in the darkness of space. It's about 100,000 light-years across. And yes, that's as enormous as it sounds. To put it in perspective, light travels at 186,000 miles per second. That means in 1 year, light covers about 6 trillion miles. And our galaxy is 100,000 of those light-years wide. Let that sink in for a moment. Even traveling at the speed of light, the fastest anything can possibly go, it would take you 100,000 years to cross from one side of our galaxy to the other. That's longer than all of recorded human history, longer than our species has existed, longer than we can truly comprehend. At the center of our galaxy sits something extraordinary and a little terrifying, a supermassive black hole. It's called Sagittarius A*, and it's more than 4 million times more massive than our Sun, just sitting there quietly, holding the galaxy together with its immense gravity, a point in space so dense, so gravitationally powerful that nothing can escape it once it gets too close, not even light. Around that center, billions upon billions of stars orbit in graceful spiral arms, beautiful, sweeping curves of starlight, like cosmic hurricanes frozen in slow motion. The Milky Way has several major spiral arms: the Perseus arm, the Scutum Centaurus arm. Each one is a dense concentration of stars, gas, and dust, regions where new stars are being born even now. And we, you and me and everyone you've ever known, we're tucked away in a small partial arm called the Orion arm, sometimes called the Orion Spur. We're about 27,000 light-years from the galactic center, not in the middle, not on the edge, but in a quiet, stable neighborhood, a safe spot where planets can form, where life can evolve, where civilizations can look up and wonder. It's actually a pretty ideal location. If we were closer to the center, near that supermassive black hole and the dense swarm of stars around it, the night sky would be incredibly bright. Millions of stars visible, radiation levels high, gravitational interactions more chaotic. Life might not have had the quiet stability it needed to emerge. And if we were too far out, toward the edge of the galaxy, there would be fewer heavy elements, less of the carbon, oxygen, nitrogen, and iron that life requires, fewer stars nearby, a lonelier part of the cosmos. But here, in the Orion Arm, conditions are just right, not too hot, not too chaotic, not too isolated. It's sometimes called the galactic habitable zone, the Goldilocks region of the Milky Way. Our Sun, along with Earth and all the other planets in our solar system, is traveling through space right now at nearly 500,000 miles per hour. 500,000 miles per hour. You're hurtling through space at that incredible speed right now. As you lie in bed, as you listen to this, you're on a cosmic journey moving faster than anything humans have ever built. And yet, even at that incredible speed, it takes us about 230 million years to complete just one orbit around the galaxy. Let that sink in for a moment. Since the dinosaurs walked the Earth, since the Triassic period when the first dinosaurs appeared, we've only made it around the galaxy once. Just once. Everything you know, every civilization that's ever existed, every pyramid built, every song sung, every war fought, every moment of human history has happened in just a tiny fraction of that single galactic orbit. We're moving through space on a timescale that makes human lifetimes look like fleeting heartbeats, like the blink of an eye in cosmic terms. When you look up at the Milky Way on a truly dark night, away from city lights, that faint band of light you see, you're looking at it from the inside. You're gazing across the thickest part of our galactic home, seeing the combined glow of billions of stars all mixed together. It's like being inside a massive disk of light, looking across its width. That's why it appears as a band rather than a sphere. We're in the plane of the disk, looking through it. And every single star you can see with your naked eyes, every constellation you've ever learned, all of them belong to our galaxy. The North Star, Orion's Belt, Sirius, the Big Dipper, all neighbours, all part of the same cosmic structure we call home. None of them are in other galaxies. They're all right here with us, fellow travellers in the Milky Way. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. That's still 25 trillion miles, but in galactic terms, it's right next door, a close neighbour. Most of the stars you see at night are within a few hundred light-years of us. That sounds like a lot, and it is, but compared to the 100,000 light-year width of the galaxy, we're seeing only the tiniest local neighbourhood. It's like standing in a city and being able to see a few blocks in each direction, not realising the city extends for hundreds of miles beyond your view. Pretty amazing when you really think about it. The Milky Way contains somewhere between 100 billion and 400 billion stars. The exact number is hard to pin down, because many stars are hidden behind dust clouds, or too faint to detect, or clustered together so densely we can't separate them. But even using the lower estimate, 100 billion stars, that's more stars in our galaxy than there are people on Earth, by a lot. If you counted one star per second, never stopping, never sleeping, it would take you over 3,000 years to count them all. And remember, that's just our galaxy. Just one galaxy. The great debate, are we alone? For a long time, and I mean hundreds of years, astronomers argued about something that seems obvious to us now. Those faint fuzzy patches visible through telescopes, the ones that didn't quite look like stars, what were they? Some people called them nebulae, from the Latin word for clouds. And honestly, that's what they looked like, soft, cloudy smudges scattered across the night sky. Some glowed faintly, others were dark patches against the starlight. Through early telescopes, they appeared as indistinct blobs, no clear edges, no distinct features, just cloudiness. Many astronomers believe these nebulae were just gas clouds within our own Milky Way, places where stars were being born, glowing with the heat of stellar formation, or maybe regions where stars had died, their outer layers blown off into space. Either way, they were part of our galaxy, part of our cosmic neighborhood, nothing more. But a few astronomers, the dreamers, the ones willing to imagine the unimaginable, they suspected something else entirely. They wondered, what if some of these fuzzy patches weren't clouds at all? What if they were other galaxies, entire island universes floating in the vast ocean of space, completely separate from our own? It was a radical idea, almost heretical, because if it were true, it would mean the universe was far, far larger than anyone had imagined. It would mean our entire galaxy, with its billions of stars, was just one among many. It would mean we weren't the center of everything, that there were other cosmic structures, other collections of stars existing beyond our reach. The debate went on for decades, back and forth, arguments in scientific journals, and at conferences, passionate discussions about the nature of reality itself. Some astronomers pointed to the spiral shapes visible in certain nebulae. Those couldn't be simple gas clouds, could they? The structure was too organized, too elegant. Others countered that we didn't fully understand how gas behaved in space. Maybe it naturally formed spiral patterns. Maybe there were processes we hadn't discovered yet. The debate became so intense that in 1920 there was a famous event called the Great Debate, held at the Smithsonian in Washington, D.C. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views. Shapley argued that the spiral nebulae were part of our galaxy. Curtis argued they were separate island universes. Neither could prove their case definitively. The telescopes of the time just weren't powerful enough to settle the question. The universe kept its secret for a few more years, and then, in the 1920s, everything changed. Edwin Hubble and the universe expands. There was this astronomer named Edwin Hubble, and in 1923 he was using the most powerful telescope in the world at the time, the 100-inch Hooker telescope at Mount Wilson Observatory in California. This telescope was a marvel of engineering, a massive instrument that could gather more light than any telescope before it. It could see fainter objects, peer deeper into space, resolve finer details. Hubble pointed it at one of those controversial fuzzy patches, the Andromeda Nebula, and he started looking, really looking, at what was inside it. Night after night, he took photographs, long exposure images that captured faint light invisible to the human eye, hours-long exposures on photographic plates, carefully developed and analyzed. And slowly, details began to emerge. He found individual stars within the nebula, not just a blur of light, but actual distinct stars, pinpoints of light that could be measured, studied, analyzed. And among those stars he found something special, a type of star called a Sepin variable. These stars pulse with a regular rhythm, brightening and dimming in a predictable pattern. Now here's why that mattered, why it was so important. A few years earlier, an astronomer named Henrietta Swan Leavitt had made a crucial discovery. She'd studied hundreds of Cepheid variables and noticed something remarkable. The rhythm of a Cephid's pulse, how fast it brightens and dims, is directly related to how bright it actually is. Its true luminosity. Slower pulsing Cephids are intrinsically brighter, faster pulsing ones are dimmer. It's like having a special type of light bulb where you can tell how powerful it is just by watching how it blinks. And if you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it must be. It's basic physics. Light spreads out as it travels. The farther away something is, the dimmer it appears. If you know its true brightness and its apparent brightness, you can work out the distance. Cepheid variables became cosmic measuring sticks, standard candles for the universe. So Hubble found these Cepheid variables in the Andromeda Nebula. He measured their pulsation periods. He calculated their true brightness. He measured how bright they appeared through his telescope, and then he did the math. The number he got shocked everyone. 2.5 million light-years away. 2.5 million light-years. Far, far beyond the edge of the Milky Way, beyond anything that could be considered part of our galaxy. The Milky Way itself is only about 100,000 light-years across, and Andromeda was 25 times farther than that. Andromeda wasn't a cloud. It wasn't a nebula within our cosmic home. It was another galaxy, an entirely separate island of hundreds of billions of stars, floating in the darkness, spinning through space on its own journey. The great debate was over. Curtis had been right. The universe was vastly larger than anyone had imagined. That discovery, that single calculation, changed everything. Overnight, the universe expanded from one galaxy to potentially countless galaxies. The cosmos had grown, and humanity had gotten smaller. But somehow, we'd also become part of something infinitely more magnificent. The floodgates opened after that. Everywhere astronomers looked, they found more galaxies, spirals like ours, ellipticals that looked like glowing footballs, irregular galaxies with chaotic, asymmetrical shapes. Some were young and blue, bursting with hot, bright stars being born from clouds of gas. Others were old and red, their star-forming days long past, filled with ancient suns quietly burning out. The universe wasn't just big, it was overflowing with galaxies, an abundance of cosmic structures, each one a universe unto itself. Each one containing billions of stars and potentially billions of planets. And maybe, just maybe, other forms of life, looking up at their own night skies and wondering the same things we wonder. A universe of shapes and stories. Now, let's take a moment to appreciate just how diverse galaxies are. When you imagine a galaxy, you might picture something like the Milky Way, an elegant spiral with graceful arms curving through space, and many galaxies do look that way. Spirals are common, beautiful, almost hypnotic in their symmetry. Spiral galaxies are busy places, active, dynamic. They're still making new stars from the gas and dust floating between their existing suns. You can see bright blue regions where massive young stars have just ignited, lighting up their cosmic nurseries with intense radiation. These young, hot stars, the blue giants, they burn incredibly bright, but don't live very long, just a few million years before they explode as supernovae. Their blue color tells us they're hot, tens of thousands of degrees on their surfaces. The spiral arms themselves aren't fixed structures. They're more like traffic jams, density waves moving through the galaxy. Stars and gas clouds move in and out of the arms as they orbit, but the pattern persists. It's like waves on the ocean. The water moves up and down, but the wave itself travels forward. The wave is a pattern, not a thing. In spiral galaxies, the arms are regions where matter gets compressed, triggering star formation, creating those bright young stars that make the spirals visible. Our Milky Way is classified as a barred spiral, meaning it has a bar-shaped structure of stars running through its center. The spiral arms extend from the ends of this bar. Not all spirals have bars. Some have arms that emerge directly from a round central bulge, but about 2/3 of spiral galaxies, including ours, have bars. Astronomers aren't entirely sure why bars form. It has something to do with gravitational interactions and the dynamics of rotating systems, but the details are still being worked out. But not all galaxies are spirals. Some are elliptical galaxies. These look like smooth, glowing spheres or stretched footballs. They don't have spiral arms or defined structures, just a smooth distribution of stars, usually older, redder stars that have been around for billions of years. Elliptical galaxies are like cosmic retirement communities. They've used up most of their gas and dust, so they're not forming many new stars anymore. They just exist, quietly aging. They're stars orbiting the galactic center in random directions rather than the organized rotation of a spiral. The largest known galaxies in the universe are ellipticals, absolutely enormous structures, sometimes containing trillions of stars, giants that form through mergers, smaller galaxies colliding and combining over billions of years. When spiral galaxies collide, the end result is often an elliptical. The collision disrupts the ordered rotation, scrambles the orbits, uses up or disperses the gas. What emerges is a more chaotic spherical distribution. Then there are irregular galaxies. These are the cosmic misfits, chaotic, asymmetrical, often the result of collisions between other galaxies, or the gravitational influence of larger neighbors pulling them out of shape. Some irregular galaxies look like they're exploding outward. Others seem to be fragments, pieces of larger structures torn apart by cosmic forces. Still others are small dwarf galaxies, never massive enough to develop clear structure. The large and small Magellanic Clouds, visible from the southern hemisphere, are irregular galaxies, small satellite galaxies orbiting our Milky Way. You can see them with the naked eye on dark nights, like faint, detached pieces of the Milky Way itself. And here's the beautiful part. Each type tells a story. Spirals tell us about ongoing star formation, about galaxies still in their prime, still creating new generations of suns and worlds. They're the young, active galaxies, full of energy and potential. Ellipticals speak of ancient history, of galaxies that have merged together or exhausted their fuel, settling into a quiet old age. They're the elders of the cosmic community. Irregulars remind us that the universe is violent sometimes, that galaxies collide and interact, that structure can be destroyed and reformed into something entirely new. They're the survivors, the works in progress. Every galaxy out there has its own personality, its own history, its own collection of hundreds of billions of stars, each potentially surrounded by planets, moons, asteroid belts, maybe even life. Some galaxies are actively forming stars at incredible rates, creating hundreds of new suns every year. Others are quiescent, quiet, their star-forming days behind them. Some contain supermassive black holes at their centers that are actively feeding, pulling in gas and dust, emitting jets of radiation that stretch for thousands of light years. These are called active galactic nuclei, and they're among the brightest objects in the universe. Others, like our Milky Way, have supermassive black holes that are relatively quiet, just sitting there, waiting, not actively feeding at the moment, but still shaping the galaxy around them with their gravity. The diversity is staggering. No two galaxies are exactly alike. The cosmic census, counting the uncountable. So, here's where we get to the heart of tonight's question. How many galaxies are there? It's a simple question with a staggering answer, and the story of how we figured it out, well, it's pretty incredible. In the 1990s, astronomers decided to do something bold, something that seemed almost crazy at the time. Some people thought it was a waste of valuable telescope time. They pointed the Hubble Space Telescope, this billion-dollar instrument orbiting above Earth's atmosphere, at a tiny patch of absolutely nothing. Not nothing like, not much there. I mean nothing. A spot in the sky that looked completely empty. No bright stars, no obvious galaxies, no clouds, no light, just darkness. A patch of sky so small that if you held a grain of sand at arm's length, it would completely cover it. A tiny speck of the night sky that appeared utterly blank. They chose a spot near the Big Dipper in what looked like an empty void between stars, and then they left the telescope's camera shutter open for 10 days straight, collecting every single photon of light that wandered into the field of view from that tiny patch of darkness. Over 100 orbits of the Earth, 342 separate exposures, nearly 100 hours of total exposure time, all focused on one minuscule piece of apparently empty sky. Many astronomers thought it was a gamble. What if there really was nothing there? What if they'd just wasted precious telescope time staring at emptiness? But when the images came back, when the data was processed and assembled, what they saw became one of the most important images in the history of astronomy. The Hubble Deep Field, that tiny patch of empty sky, that speck no bigger than a grain of sand held at arm's length, contained over 3,000 galaxies. 3,000 galaxies. Each one a massive structure containing hundreds of billions of stars, each one a complete universe of suns and potentially planets. Some were relatively close by cosmic standards, maybe a few 100 million light-years away. Others were so distant that their light had been traveling for over 12 billion years, leaving those galaxies when the universe was still young and hot. The image showed galaxies in every stage of evolution, young blue galaxies forming stars at furious rates, mature spirals like our own Milky Way, ancient ellipticals glowing red with old stars, bizarre shapes, galaxies mid-collision, fragments and mergers. It was like taking a core sample through cosmic time. Every distance revealed galaxies from a different era, a different age of the universe. And remember, this was just one tiny patch, one grain of sand's worth of sky. If that tiny patch held so many galaxies, imagine the entire sky. Imagine all the patches like that one, covering every direction you could look. The math was staggering. Astronomers did similar deep observations in other parts of the sky and found the same thing. Thousands of galaxies in every direction. The universe was far more crowded than anyone had realized. Based on these deep field observations, taking small samples and multiplying them across the entire visible sky, astronomers calculated the total number of galaxies. The estimate they arrived at was almost incomprehensible. At least 2 trillion galaxies in the observable universe. 2 trillion. That's a 2 with 12 zeros after it. 2,000, thousand galaxies. Let me help you wrap your mind around that number for a moment. If you counted one galaxy per second, never stopping, never sleeping, it would take you over 63,000 years to count them all. There are more galaxies in the universe than there are grains of sand on all the beaches on Earth. Think about that. Every grain of sand on every beach, and there are still more galaxies. There are more galaxies than there are stars visible to your naked eye in the night sky, by many billions of times over. Each galaxy contains anywhere from a few million to several trillion stars. If we use an average of 100 billion stars per galaxy, that means the universe contains roughly 200 billion trillion stars. That's 200 sextillion stars, a number so large it loses meaning. And remember, that's just what we can see, just the observable universe. The observable universe is limited, not because the universe ends at some boundary, but because light has only had a finite amount of time to travel since the Big Bang. The universe is about 13.8 billion years old. Light travels very fast, but even at that speed, light from regions farther than about 46 billion light-years away hasn't reached us yet. Yes, 46 billion light-years, even though the universe is only 13.8 billion years old. That's because space itself has been expanding. The light has been traveling for 13.8 billion years, but space stretched during that time, so those galaxies are now much farther away. It's complicated, but the point is, we can only see so far. Beyond that lies more universe, more space, and almost certainly more galaxies. The true number might be infinite. We don't know if the universe is finite or infinite. We don't know if it curves back on itself or extends forever. But even the conservative estimate, 2 trillion galaxies in just the observable universe, is overwhelming. The universe didn't create a few galaxies scattered here and there. It created an abundance, an overwhelming multitude, a cosmic population beyond comprehension. Looking back through time, here's something that's going to shift your perspective even more. When you look at distant galaxies, you're not seeing them as they are right now. You're seeing them as they were, sometimes billions of years ago. Light takes time to travel. It moves incredibly fast, the fastest speed possible in our universe. But the distances are so vast that even light needs time to cross them. The light from your bedroom lamp reaches your eyes almost instantly. The light from the moon takes about 1.3 seconds, from the sun about 8 minutes. But from the nearest star beyond our sun, 4 years. From the Andromeda galaxy, 2.5 million years. From distant galaxies captured in the Hubble Deep Field, over 13 billion years. That means when you look at a galaxy 10 billion light-years away, you're seeing it as it was 10 billion years ago, not as it is now, as it was. Think about what that means. That galaxy might look completely different today. It might have collided with another galaxy and merged into something larger. It might have exhausted its star-forming gas and faded into quiet old age. It might have developed new spiral arms or lost old ones. But you'll never see that version. The light showing you what that galaxy looks like today won't arrive for another 10 billion years. By then, Earth might not exist anymore. The sun will have expanded into a red giant and swallowed the inner planets. Humanity will be long gone, either extinct or evolved into something unrecognizable. Every photograph of distant galaxies is a photograph of the past, a window into cosmic history, a fossil record written in light. The universe is so vast that looking into space is the same as looking back through time. Distance and time become intertwined. Every direction you look, you're seeing the universe at a different age. When astronomers create maps of galaxy distributions, they're not just mapping space, they're mapping space-time itself, showing where galaxies were at different moments in cosmic history. The nearest galaxies appear as they were relatively recently, maybe a few million years ago, nothing in terms of cosmic time. Middle-distance galaxies show us what the universe looked like a few billion years ago, when star formation was at its peak, when galaxies were more active, more chaotic, colliding more frequently. And the farthest galaxies, those faint red smudges at the very edge of detection, they're snapshots from the universe's infancy, from a time when the first galaxies were just forming, when everything was closer together, when the cosmos was young and hot. It's like looking at a family photo album where every picture was taken in a different decade, but somehow you're seeing them all at once, all the ages, all the stages of development. Astronomers study these distant galaxies to understand how galaxies evolve, how they change over time, how they looked in the past versus how they appear today. The early universe was different. Galaxies were smaller, less organized, colliding more often. There was more gas available for star formation. Everything was more chaotic. Over billions of years, things settled down. Galaxies grew larger through mergers. They exhausted their gas supplies. The rate of star formation declined. Structure emerged from chaos. The universe matured like a living organism growing from youth to adulthood. And we can see that entire story just by looking at galaxies at different distances, different times, different ages of the cosmos. Every time we look at the night sky, we're not just seeing space, we're seeing history. We're witnessing the universe's story unfold across billions of years, all at once. The new window, James Webb Space Telescope. Recently, humanity opened a new window to the universe, a window that sees even farther, even deeper than ever before. The James Webb Space Telescope launched on Christmas Day, 2021, and by mid-2022, it started sending back images that left astronomers speechless, images that were somehow both expected and completely surprising. Webb is different from Hubble, where Hubble primarily observes visible light, the light our eyes can see. Webb observes infrared radiation, heat radiation, light with wavelengths longer than what we can see, and that difference is crucial. Here's why. The universe is expanding, and as it expands, light traveling through space gets stretched. Its wavelength increases. It shifts toward the red end of the spectrum. Astronomers call this redshift, and the farther away something is, the faster space is expanding between us, the more its light gets stretched. For the most distant galaxies from the early universe, their light has been traveling for over 13 billion years, and space has been expanding that entire time. What left those galaxies as visible light, ultraviolet and blue, arrives at us stretched into infrared, light our eyes can't see. Hubble could see some infrared, but it was limited. It was designed primarily for visible light. Webb, on the other hand, is optimized for infrared. It can see what Hubble couldn't. It can peer into the earliest epochs of the universe, when the first galaxies were forming, when the cosmos was still very young. And what it's finding is surprising. Galaxies in the early universe are bigger than expected, brighter than predicted, more organized than our models suggested. According to our theories, galaxies should have been small and chaotic in the early universe, building up gradually over billions of years through mergers and accretion. But Webb is finding large, well-structured galaxies existing when the universe was less than 1 billion years old, sometimes just a few 100 million years after the Big Bang. It's like opening a history book, expecting to read about primitive cave dwellings and discovering evidence of sophisticated cities. The universe was busy right from the start, creating stars faster, assembling galaxies more efficiently than we thought possible. It means our models need to be revised. Our understanding needs to evolve. There are processes we don't fully comprehend, mechanisms for galaxy formation that work faster than we realized. And that's exciting, because it means there's still so much to learn, so many mysteries left to solve. Every time we build a better telescope, the universe reveals another layer, another secret, another surprise. It's been like this throughout history. Every technological leap, from Galileo's simple telescope to Hubble to Webb, has shown us something unexpected. The universe keeps teaching us that what we know is just a fraction of what's really out there, that our models are approximations, our theories incomplete. There are always more mysteries waiting, always deeper questions, always another horizon to explore. And honestly, that's kind of comforting. The universe isn't running out of wonders. It's not becoming fully known. There will always be more to discover, always something new to marvel at. As long as we keep looking, keep asking questions, keep building better tools, the cosmos will keep revealing its secrets. One layer at a time. You are made of stars. Now let me bring this all closer to home for you. Literally. Every atom in your body, the iron in your blood, the calcium in your bones, the oxygen you're breathing right this very moment, all of it was forged inside stars. Stars that lived billions of years ago, stars that burned brightly in galaxies scattered across the cosmos, stars that eventually ran out of fuel, collapsed under their own gravity, and exploded in supernova events so powerful they outshone entire galaxies. Those explosions, those cosmic fireworks, created heavy elements, elements heavier than hydrogen and helium. In the cores of stars, hydrogen fuses into helium. That's what powers them, what makes them shine. The fusion releases energy, and that energy pressure balances against gravity, keeping the star stable. But as stars age, they start fusing helium into heavier elements, carbon, nitrogen, oxygen. In the cores of massive stars, over many stages, fusion creates neon, magnesium, silicon, sulfur, all the way up to iron. Iron is where fusion stops being profitable. Fusing iron takes more energy than it releases. So when a massive star's core turns to iron, fusion stops, the energy pressure disappears, and gravity wins. The core collapses in less than a second, then rebounds. The outer layers crash inward, hit the rebounding core, and bounce back outward in a catastrophic explosion. A supernova. For a brief time, sometimes just a few weeks, that single exploding star can outshine its entire galaxy. Billions of stars, and one dying star is brighter than all of them combined. And in that explosion, in the incredible temperatures and pressures, even heavier elements are created. Elements like copper, zinc, gold, silver, uranium. All the elements heavier than iron in your body. The trace metals, the rare elements. They were created in supernovae, in the deaths of massive stars. Those explosions scattered stardust across space, clouds of gas enriched with heavy elements, debris from stellar death, seeding the cosmos with the ingredients for new worlds. That dust eventually gathered into new molecular clouds, which collapsed under gravity to form new stars, and around those new stars, from the remaining dust, planets formed. Rocky planets like Earth, made from the debris of earlier generations of stars. The iron core of our planet, the iron in your blood, came from stars that died before our sun was born. The calcium in your bones, forged in stellar cores, scattered by supernovae, gathered into the dust cloud that became our solar system. The oxygen you're breathing, created by fusion in massive stars, released when they exploded. You're not separate from the galaxies. You're made of them. You're stardust that learned to think, to wonder, to look up at the night sky and ask, how many? Where did I come from? What else is out there? So when you think about those 2 trillion galaxies out there, remember, you're connected to all of them. The same physics, the same chemistry, the same processes that create stars and galaxies created you. The galaxies aren't just out there somewhere, they're inside you too, in every atom, in every breath. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. Think about that. The universe, through you, through your consciousness, is experiencing itself, observing itself, understanding itself. The same atoms that were once scattered in interstellar space are now arranged in such a way that they're aware, they can think, they can feel, they can wonder. That's extraordinary. That's profound. You're not just in the universe. You are the universe experiencing itself from one particular point of view. And somewhere out there, maybe in one of those 2 trillion galaxies, maybe on a planet orbiting a star you'll never see, there might be someone else. Another arrangement of stardust that's also aware, also wondering, also looking up at their night sky and asking the same questions. What a beautiful thought to drift off to sleep with. The invisible architecture. Now, here's where things get even more mysterious. Most of the universe isn't even made of the stuff we can see. The galaxies, the stars, the planets, all the light and matter we've been talking about makes up less than 5% of the total content of the universe. 5%. Let that sink in for a moment. Everything we see, every telescope image, every star in the night sky, all of it is just the visible tip of something much larger and stranger. About 27% of the universe is made of something called dark matter, and roughly 70% is an even more mysterious force known as dark energy. Together, they dominate the cosmos, determining its structure, its fate, its very nature. The galaxies we see are like islands of light floating in an unseen ocean, shaped and sustained by dark currents beneath them. Dark matter, the hidden framework. The concept of dark matter emerged from a simple but puzzling observation. When astronomers measured how fast galaxies rotate, they found something strange. The stars at the edges of galaxies, the ones far from the center, were moving too quickly. According to Newton's laws of gravity, the visible mass, the stars, gas, and dust we could see, wasn't enough to hold them in orbit. By all accounts, those outer stars should have been flung out into space. The galaxies should have torn themselves apart. And yet, they remained intact, spinning peacefully, holding together. The only explanation was that there must be more matter present than what we could see, invisible mass, adding gravity, holding everything together. This unseen substance became known as dark matter. It's one of the most profound discoveries in modern science, not because we've detected dark matter directly, we haven't, but because its presence can be measured through its effects. Light bends as it passes near massive objects, a phenomenon known as gravitational lensing. When light from distant galaxies travels toward us, it curves around the mass between us and them. By studying how that light is distorted, how background galaxies appear stretched and warped, astronomers can map where the hidden mass lies. The results are striking. The visible galaxies trace only part of the cosmic structure. Around and between them are vast halos and filaments of dark matter, stretching across the universe like an invisible web. The galaxies we see are simply the brightest nodes on that invisible lattice, the decorations on a much deeper architecture. Within our own galaxy, dark matter surrounds us. The Milky Way is embedded in a halo of it, extending far beyond the visible disk of stars. We move through this invisible field constantly, unaware. Dark matter doesn't interact with light or ordinary matter in any significant way, so it passes through everything, planets, people, telescopes, without leaving a trace we can detect, except through gravity. It's as if we live inside an invisible architecture that holds everything in place. The stars, the gas, the planets, even the shape of the galaxy itself, all of it is determined by this unseen scaffolding. If dark matter vanished tomorrow, galaxies would unravel. The stars would drift apart, the cosmic web would dissolve, and the universe would look nothing like it does now. And maybe, somewhere in one of those 2 trillion galaxies, on a planet orbiting a sun we'll never see, there's someone else, another conscious being, looking up at their own night sky, wondering the same things you're wondering. Are we alone? How many galaxies are there? What does it all mean? The universe is not a static photograph. It's a living process, always changing, always evolving, always creating new patterns from old elements. And you're part of that process, not just observing it, but participating in it. Your thoughts, your awareness, your wonder, those are part of the universe's ongoing evolution. Consciousness, as far as we know, is the universe's way of looking at itself, of knowing itself, of appreciating its own beauty. And tonight, through your eyes, the universe is seeing those 2 trillion galaxies, feeling awe at its own vastness, wondering about its own nature, letting the mystery settle, So, as you drift deeper now, as your breathing slows, as your thoughts begin to blur at the edges, let all of this settle over you like a soft blanket. 2 trillion galaxies, maybe more, maybe infinitely more. Each one a spiral of light, each one containing billions of stars, each one a universe unto itself. And here you are in one of them, on a small planet, orbiting an ordinary star in a quiet arm of the Milky Way. You're small, yes, but you're also extraordinary, rare, conscious, aware. You don't have to understand everything. You don't have to hold all these numbers in your mind. Just let the feeling remain. The sense of scale, the connection. You're part of something immense, something ancient, something beautiful. Above you, around you, within you, the universe hums softly, expanding, evolving, creating, wondering. The galaxies will still be there tomorrow, still spinning, still glowing, billions of years old, and they'll be there billions of years from now. But this moment, right now, is yours. Your brief flicker of awareness in the cosmic dark, your chance to notice, to wonder, to feel connected. Close your eyes now, let your shoulders relax completely. Feel the weight of your body sinking into whatever you're resting on. Your stardust, your cosmos, your small and infinite all at once. The light from distant galaxies is still traveling, still crossing the void. Some of it, light that left its source billions of years ago, is reaching Earth right now, falling gently through the atmosphere, landing on soil and ocean and cities. You're bathed in ancient starlight, surrounded by cosmic history, connected to everything that's ever been. And as dark energy continues pushing space apart, as the universe keeps expanding, as galaxies drift slowly toward their distant futures, you get to rest here, in this moment, in this small corner of an infinite cosmos. The universe isn't asking you to solve its mysteries tonight. It's simply inviting you to be part of them, to rest within them, to let them cradle you into sleep. So rest now, dream deep, and know that you're exactly where you belong, in a universe that's stranger and more wonderful than we ever imagined. The question of infinity. There's one more mystery that's worth pondering as your eyes grow heavier. Is the universe infinite or finite? It's one of those questions that feels almost impossible to answer, and yet it matters, because the answer determines whether those 2 trillion galaxies we can see are all there is, or just the beginning of something much, much larger. The observable universe has a boundary, but that's not an edge where space ends. It's just the limit of how far light has had time to reach us since the Big Bang. Beyond that horizon, there's almost certainly more space, more galaxies, more stars. But does it go on forever, or does it eventually curve back on itself, like the surface of a sphere? Current measurements suggest the universe is flat, or very, very close to flat. And in a flat universe, according to our best theories, space extends infinitely in all directions. If that's true, then there aren't just 2 trillion galaxies. There are infinitely many, an endless ocean of cosmic structures stretching forever through space. It's hard to even conceive of that. Infinity isn't just a very large number, it's something categorically different. No matter how many galaxies you count, there are always infinitely more. And if the universe is infinite, then somewhere out there, incredibly far away, there might be another galaxy exactly like the Milky Way. Another Earth, another version of you, lying in bed, listening to these same thoughts. It sounds like science fiction, but in an infinite universe, every possible arrangement of matter must occur, not just once, but infinitely many times. Of course, we may never know for certain. The parts of the universe beyond our cosmic horizon are forever unreachable. Their light will never reach us because space is expanding too fast. But the possibility remains. The possibility that the universe doesn't end, that it continues and continues without limit. It's both terrifying and beautiful to be so small in something so vast, and yet to be conscious of it. To be able to think about infinity even if we can't truly grasp it. Cosmic loneliness and cosmic company. There's a paradox at the heart of our cosmic situation. On one hand, the universe is almost unimaginably vast. 2 trillion galaxies at minimum, possibly infinitely more. Billions upon billions of stars, countless planets. With all that abundance, statistically, we shouldn't be alone. Life should be common. Intelligence should have emerged in countless places. The galaxy, the universe, should be teeming with civilizations. And yet, we haven't heard anything. No signals, no visitors, no unmistakable evidence of anyone else. The silence is profound and a little unsettling. Maybe we're early. Maybe we're among the first intelligent species to emerge. Maybe the universe is still young, still warming up, and in a few billion years, the cosmos will be filled with voices. Or maybe intelligence is rare. Maybe the jump from simple life to consciousness requires such a specific set of circumstances that it happens only once every few trillion galaxies. Or maybe civilizations don't last. Maybe intelligence carries within it the seeds of its own destruction. Maybe every species that reaches our level eventually destroys itself through war, environmental collapse, or technologies it can't control. That's a sobering thought, but it's also a call to action. If we want to be one of the species that makes it, that endures, that spreads beyond its home world, we need to be careful, thoughtful, wise. Or maybe, and this is perhaps the most intriguing possibility, maybe we're looking in the wrong way. Maybe life is all around us, but so different from what we expect that we don't recognize it. Maybe consciousness can emerge in forms that don't need planets, or oxygen, or even matter as we understand it. Maybe the universe is filled with minds we can't comprehend, operating on timescales, or in dimensions we haven't considered. The truth is, we don't know, and that uncertainty is part of what makes the search meaningful, part of what keeps us looking up at the night sky with wonder. Even if we're alone, even if Earth is the only place where life managed to organize itself into something conscious that makes us incredibly precious, it means we carry the universe's self-awareness. We are how the cosmos knows itself. And if we're not alone, if somewhere out there in those 2 trillion galaxies, there are others looking up and wondering, then someday, maybe, we'll find each other. What a moment that would be. What a transformation of human understanding. The rhythm of deep time. Let's zoom out one more time, not in space, but in time. The universe is 13.8 billion years old. That's the time that's passed since the Big Bang, since the moment when space and time and matter all began. 13.8 billion years. It's an incomprehensible time span. If you counted one number per second, it would take you over 437 years just to count to 13.8 billion. And yet, as vast as that time span is, it may be just the beginning. The universe might continue for trillions upon trillions of years, maybe forever. The age of stars, the era we're living in now, where galaxies shine brightly and new suns are born, this might be just a brief, brilliant phase in cosmic history. Eventually, billions of years from now, the stars will start to go out. One by one, the universe will grow darker, colder, more spread out. In 4 billion years, our sun will expand into a red giant. It'll swallow Mercury and Venus, maybe Earth too. The oceans will boil away. The atmosphere will be stripped. Our blue marble will become a scorched rock. But that's okay, because by then, if humanity survives, we'll have spread beyond this single world. will have found new homes among the stars. In 4 billion years after that, the Milky Way will collide with Andromeda. The two galaxies will dance around each other for millions of years, eventually settling into a new structure, a merged galaxy with a different shape, a different name. The night sky will be unrecognizable, but there will still be stars, still planets, still the possibility of life and consciousness. Over trillions of years, star formation will slow. The gas and dust needed to make new stars will be used up. Existing stars will burn out. The galaxies will gradually dim. Black holes will evaporate through Hawking radiation, slowly, over time scales, so vast they make the current age of the universe seem like a blink. 10 circumflex, 100 years, a Google years, time spans with no human analogy. Eventually, the universe will reach a state called heat death, maximum entropy, everything spread out, everything the same temperature, no energy gradients left to power any process, no stars, no planets, no structure, just a thin soup of particles expanding forever in the dark. It sounds bleak, but remember, this is so far in the future that it's almost meaningless. The time between now and then is longer than all of cosmic history so far, multiplied by itself, again and again. For now, for an almost unimaginably long now, the universe is alive, bright, full of potential, full of beauty, and we get to be here for it. In this brief, brilliant era when stars shine and galaxies swirl and consciousness has emerged to witness it all. The gift of this moment. Every discovery of a new kind of light, a new kind of signal, adds another layer to how the universe grows with us. When we detected gravitational waves for the first time in 2015, we weren't just confirming a century-old prediction from Einstein's theory of general relativity. We were opening an entirely new sense, one that lets us hear the vibrations of space-time itself. These ripples, created by the collision of black holes or neutron stars, travel through the cosmos at the speed of light. They carry no light at all, no electromagnetic radiation whatsoever. Yet they tell us about events otherwise completely invisible. It's another way the universe grows before us, not through more stars or galaxies being created, but through new ways of knowing what already exists. Soon, other kinds of observatories will add to this expansion of perception. Neutrino detectors buried deep in Antarctic ice, listening for ghostly particles that pass through entire planets without slowing. Light alone can't create structure on the scales we see. The dark provides the framework. It's ironic, really, that what we call dark matter is what gives the universe its shape, its texture, its ability to exist in the way it does. The light we see, beautiful and familiar, is only the decoration on a much deeper pattern. What is dark matter? And yet, for all our understanding of its effects, we still don't know what dark matter actually is. It's not made of atoms. It doesn't emit radiation. It doesn't collide or clump in the same way normal matter does. The leading theories suggest it might be composed of exotic particles, things called WIMPs, weakly interacting massive particles, or axions, or something even stranger we haven't yet imagined. Experiments deep underground and in space are searching for these particles, trying to catch the faintest whisper of interaction. So far, nothing conclusive has been found. The universe is keeping its secret. There are even galaxies made almost entirely of this hidden substance. Astronomers have discovered systems where stars are sparse, but gravitational effects are strong, suggesting that the visible matter is only a thin trace on top of a vast dark foundation. These dark galaxies contain few stars, yet they move as if filled with enormous amounts of mass. In some cases, they barely glow at all, detectable only through the gravitational lensing of background light. They're like ghosts, shapes in space inferred from the way they bend what passes behind them. Most galaxies, including our own, are surrounded by massive halos of dark matter. These halos are enormous, far larger than the visible parts of the galaxies themselves. The stars and gas we can see make up only the central regions, a luminous core within a dark sphere. When galaxies collide, their dark matter halos interact too, merging and stretching into long filaments. The visible fireworks of star formation that follow, the bright bursts and tidal tails, are only the surface effects. The real dynamics happen in the invisible mass beneath, where gravity sculpts the encounter. In large-scale simulations of the universe, dark matter is the first ingredient. The models start with a nearly uniform field of particles, then let gravity do its work. Over billions of years, the dark matter collapses into filaments and clumps, forming the skeleton of the cosmic web. Normal matter, the atoms that form stars and galaxies, falls into these gravitational wells, collecting along the same structures. Without the dark, the light would have nowhere to gather. Every galaxy you see owes its existence to this invisible framework. Dark energy, the accelerating universe. And then there's dark energy, which is even stranger. In 1998, astronomers made a discovery that shocked everyone. They were studying distant supernovae, exploding stars that can be seen from billions of light years away. They expected to find that the universe's expansion was slowing down. After all, gravity should be pulling everything back together, right? But what they found was the opposite. The universe's expansion is accelerating. It's speeding up. Something is pushing space apart, overpowering gravity on the largest scales. And whatever it is, it makes up about 70% of the universe's total energy. They called it dark energy. And honestly, we have no idea what it is. It's not matter. It's not radiation. It's something else entirely. Some kind of energy woven into the fabric of space itself. The more space expands, the more dark energy there is, which makes the expansion accelerate even faster, which creates more space, which creates more dark energy. It's a runaway process, and it means that the universe's future is very different from what we once thought. Billions of years from now, the expansion will have carried distant galaxies so far away that their light will no longer reach us. The universe will appear emptier, lonelier. Eventually, only our local group of galaxies will remain visible. Everything else will have receded beyond the cosmic horizon. The night sky will darken. The universe will feel smaller again, even though it's actually larger than ever. It's a strange and melancholy fate, but it's also billions of years away. For now, the universe is still filled with light. The cosmic web. When you zoom out far enough, when you look at the universe not galaxy by galaxy, but as a whole, a pattern emerges. Galaxies aren't scattered randomly. They cluster together along invisible threads, forming what astronomers call the cosmic web. Imagine spiderwebs stretched across the universe. Galaxies gather along the strands, forming bright nodes where thousands of galaxies collect. Between the strands lie vast voids, regions hundreds of millions of light years across with almost nothing in them. These voids aren't truly empty. They contain some faint galaxies, scattered gas, and dark matter, but compared to the dense filaments, they're almost barren. The cosmic web is shaped by dark matter, that invisible substance we talked about earlier. Dark matter forms the scaffolding, and galaxies build themselves along it. If you could see dark matter, the universe would look like a three-dimensional foam, filaments connecting nodes, surrounding bubbles of emptiness. It's beautiful in an abstract way, like looking at the structure of cells under a microscope, or the neural networks in a brain. The universe, it turns out, has structure all the way up, from planets to stars, from stars to galaxies, from galaxies to clusters, and from clusters to the cosmic web itself. Each level builds on the one below it, and each one follows the same fundamental rules. Gravity pulls things together, and expansion pushes them apart. The balance between these forces determines the shape of everything. Galaxy collisions and mergers. Galaxies, despite their vastness, don't exist in isolation. They interact, they collide, they merge. Right now, our Milky Way is on a slow-motion collision course with the Andromeda Galaxy. The two are approaching each other at about 250,000 miles per hour. That sounds fast, but given the distance between us, the collision won't happen for another 4 billion years. When it does, it will be spectacular, but not in the way you might imagine. Galaxies aren't solid objects. They're mostly empty space. The distances between stars are so enormous that when two galaxies collide, their stars rarely hit each other. It's like throwing two swarms of fireflies together. They pass through each other, mingling, swirling, but individual fireflies almost never touch. What does happen is that the galaxy's shapes distort. Gravity pulls on everything. Spiral arms stretch into long tidal tails. Gas clouds slam together, triggering massive bursts of star formation. The night sky, for any observers still around, would fill with brilliant new stars, glowing nebulae, and the combined light of two galaxies merging into one. Eventually, over hundreds of millions of years, the Milky Way and Andromeda will settle into a new form, probably an elliptical galaxy. Astronomers have already given it a name: Milkomeda. It sounds almost whimsical, but it's also a reminder that even galaxies, these enormous ancient structures, are not permanent. They change, they evolve, they live and die, just on timescales that make human history look like a blink. The future of galaxies. Let's talk about the future for a moment. What will happen to all these galaxies over the next trillion years? Stars will keep forming, but eventually the gas will run out. Galaxies will exhaust their fuel, star formation will slow, then stop. The universe will enter what's called the age of degeneration. Existing stars will keep burning, but no new ones will be born. Over trillions of years, those stars will die. The massive ones will explode as supernovae. The smaller ones will fade into white dwarfs, then cool into black dwarfs. Galaxies will become darker, filled with dead stars, black holes, and faint remnants. Eventually, even the black holes will evaporate. Through a process called Hawking radiation, they'll slowly leak energy back into space until they disappear entirely. In the end, the universe will be cold, dark, and nearly empty. Just a thin soup of particles drifting through an ever-expanding void. It's called heat death, the final state of a universe that has run down, used up all its energy, and settled into maximum entropy. It sounds bleak, but it's also unimaginably far in the future. We're talking about timescales so long that they make the current age of the universe look like a heartbeat. For now, for the next many billions of years, the universe is still young, still vibrant, still filled with galaxies making stars, planets forming, and maybe life emerging. Are we alone? With 2 trillion galaxies, each containing billions of stars, the question becomes almost unavoidable. Are we alone? Statistically, it seems almost impossible. If even a tiny fraction of stars have planets, and even a tiny fraction of those planets have life, the universe should be teeming with it. And yet, we haven't found anyone. No signals, no visits, no undeniable proof. This is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" There are many possible answers. Maybe life is incredibly rare. Maybe intelligent life is even rarer. Maybe civilizations don't last long, destroying themselves or fading away before they can reach out. Maybe the distances are just too vast. Even at the speed of light, traveling between galaxies would take millions of years. Or maybe life is common, but so different from us that we don't recognize it. Maybe it exists in forms we can't imagine, using chemistries we've never considered. The truth is, we don't know. But the search continues. Telescopes scan the skies for signals. Spacecraft explore our solar system. Scientists study extremophiles on Earth, life that survives in boiling water, frozen ice, and toxic chemicals, expanding our understanding of what's possible. Every new exoplanet we discover, every potentially habitable world, brings us closer to an answer. And even if we never find anyone, the search itself is meaningful, because it helps us understand our place in the cosmos. The privilege of awareness. Here's something worth sitting with for a moment. You right now, lying in bed or sitting quietly, you are a collection of atoms that came from stars. Those atoms formed in the hearts of suns were scattered across space by supernovae, gathered into new clouds, formed new stars and planets, and eventually, you're made of stardust, literally. But it's more than that. Those atoms, carbon, nitrogen, oxygen, iron, they're not just in you, they are you. Every thought you're having right now is the result of electrical signals moving through neurons made of recycled stardust. The iron in your blood was forged in a dying star. The calcium in your bones came from a supernova explosion. The oxygen you're breathing was created in stellar fusion billions of years ago. Every part of you is ancient, recycled from generation after generation of stars. And now, those atoms are arranged in such a way that they're aware. They can think, they can wonder, they can look up at the night sky and ask questions. The universe, through you, is experiencing itself. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. Think about that for a moment. The same laws of physics that govern galaxies govern you. The same atoms that make up distant stars make up you. You're not separate from the universe. You're part of it, deeply, intimately connected. The galaxies don't know they exist. They spin and shine, but they don't wonder why. They don't ask questions. They don't feel awe. You do, and that awareness is one of the most remarkable things in the universe. Out of all those 2 trillion galaxies, out of all those billions upon billions of stars, out of all the planets and moons and asteroids, somehow, on this one small world, matter organized itself into something that can think, something that can appreciate the beauty of a sunset, something that can feel love, something that can wonder about its own origins. That's extraordinary. That's profound. A quiet kind of belonging. You know, there's something deeply comforting about scale. When you realize how vast the universe is, how many galaxies exist, how old everything is, your daily worries start to feel a little lighter. That argument you had, that deadline you're stressed about, that embarrassing thing you said 3 years ago that still keeps you awake sometimes. In the context of 2 trillion galaxies, in the context of 13.8 billion years, those moments are so small, so fleeting, not unimportant. Your feelings matter, your life matters, but perspective helps. The universe has been here for an unimaginably long time, and it will continue for an unimaginably long time after we're gone. Galaxies will keep spinning, stars will keep burning, space will keep expanding. And yet, right now, in this brief moment, you get to be part of it. You get to witness it. You get to think about it and feel wonder. That's a privilege, a cosmic gift. So, when you feel small, remember that small doesn't mean insignificant. You're a conscious arrangement of atoms in a universe that's mostly unconscious matter, that makes you rare, special, meaningful. You're stardust that woke up, that learned to wonder, that can look at the night sky and feel connected to something greater. The galaxies aren't just out there somewhere, they're inside you too, in every atom, in every breath, in every thought you have about them. The observable and the unknown. Here's one more mystery to drift off with. Everything we've talked about tonight, those 2 trillion galaxies, that's just the observable universe, just the part we can see. The observable universe has a boundary, not a physical edge, but a limit defined by time and light. Light from regions farther than about 46 billion light-years away hasn't had time to reach us yet. So we can't see those regions, not because they don't exist, but because their light is still on its way. But that doesn't mean the universe stops there. Most cosmologists believe the universe extends far beyond what we can see, maybe infinitely. Maybe it curves back on itself. Maybe it branches into other regions with different physical laws. We don't know. We can't know. Not yet, anyway. What we do know is that the part we can see, the observable universe, is just a tiny bubble in something much larger. And that bubble contains at least 2 trillion galaxies. If the universe is infinite, then there are infinite galaxies, infinite stars, infinite planets, infinite possibilities. It's dizzying to think about, but also strangely comforting, because it means that no matter how much we discover, there will always be more. The universe will never run out of wonders, never become fully known, never stop surprising us. There will always be another horizon to explore, always deeper questions to ask, always new mysteries waiting at the edge of our understanding. The dance continues. Somewhere right now, at this very moment, stars are being born in distant galaxies. Clouds of gas and dust are collapsing under their own gravity. Temperatures are rising. Nuclear fusion is igniting. New suns are lighting up for the first time. Somewhere else, stars are dying. Massive suns are running out of fuel, collapsing, exploding as supernovae, scattering their enriched material across space to seed future generations. Galaxies are colliding, merging, creating spectacular bursts of star formation, stretching each other into long tidal tails of stars and gas. Black holes are feeding, planets are forming, asteroids are colliding, solar systems are being born. Telescopes that measure cosmic rays, the highest energy particles in the universe. Instruments that watch for fast radio bursts, mysterious flashes from across the cosmos that we're only beginning to understand. Each one opens a different window into reality. The universe is not silent. It turns out, it speaks in many languages, wavelengths we can't see, particles we can barely detect, gravitational whispers that shake the fabric of space. And with each new translation, our picture of the cosmos becomes richer, more nuanced. It's not that the universe itself becomes larger, exactly. It's that our awareness of its complexity keeps deepening, layer after layer, like a painting that reveals more detail the longer you look at it, the closer you lean in. The patience of light. Sometimes it's easy to forget just how new all of this is. The light we collect today will still be traveling tomorrow, next year, 1,000 years from now. The universe doesn't hurry for anyone. It offers itself slowly, patiently, photon by photon, to anyone willing to wait and watch. And we, in our brief lifetimes, do what we can to catch those signals, to assemble them into meaning, to build a picture of something far larger than ourselves. The telescopes we build now may show future generations galaxies we can't even imagine yet. They will see farther than we ever could, and the universe will grow again in their minds, just as it grew in ours. There's a quiet symmetry to all of this, a balance. The cosmos expands physically, space itself stretching with time as dark energy pushes everything apart. At the same moment, our awareness expands too, pushed outward by curiosity and wonder. The two growths mirror each other perfectly. One is cosmic, one is cognitive. Together they create the experience we call discovery. Each time we build a better eye, sharper and more sensitive, the universe reveals a new layer of itself, like curtains being drawn back one by one. It's as if the cosmos has been waiting all along for us to learn how to see it properly, growing into the universe. When you think of it that way, it's not really that the universe grows with our eyes. It's that our eyes finally grow into the universe. Our instruments extend our sight beyond what evolution gave us. Our minds interpret the patterns, finding order in chaos, and slowly, steadily, the boundary between what is known and what is possible moves outward. Inch by inch, generation by generation. The galaxies don't multiply because of us, of course, but our understanding of them does. Each image, each survey, each piece of carefully gathered data adds to the tapestry, making it denser, more intricate, more alive with meaning. And even as we reach these new heights of vision and understanding, the process remains grounded in something profoundly, beautifully human. Curiosity. That's what drives it all. The same impulse that made ancient astronomers chart the stars with nothing but their naked eyes and careful records. We've built incredible machines to do it better, faster, with more precision. But the instinct underneath is unchanged, timeless. To look into the dark and wonder what's there, to ask if the light will reveal more, to keep watching even when the night seems endless, and the answers seem impossibly far away. The unfinished story. So the universe grows, and we grow with it. Not by adding more matter or more light to what exists, but by deepening our ability to perceive what was always there. The galaxies were always present, shining in the darkness. The light was always on its way, traveling toward us. We simply needed time to build the tools we needed, time to learn how to listen to what the cosmos was saying, time to realize that seeing is not at all the same as knowing, and that knowing is never truly finished. The horizon keeps moving farther away. The universe keeps unfolding before us, and every time we open our eyes a little wider, a little more clearly, it opens with us. Your breathing is slower now, isn't it? Your thoughts drifting like clouds across a quiet sky. That's perfect. That's exactly where you should be. The universe isn't asking anything of you tonight. It's not demanding that you understand everything or remember every detail. It's simply inviting you to rest within its vastness, to feel connected to something ancient and ongoing. The light from distant galaxies continues its journey. Some of it, photons that left their source billions of years ago, are arriving at Earth right now, this very moment, falling through the atmosphere, landing on oceans and mountains and cities. And maybe, just maybe, a few of those ancient photons are landing on you. You're bathed in starlight, surrounded by the universe's patient storytelling. And as you sink deeper into rest, as your body grows heavy and your mind grows quiet, know that you're part of this story too. You're not just observing the cosmos, you're participating in it. Your consciousness, brief as it is one of the ways the universe experiences itself. So rest now. Let go. Allow yourself to drift. The galaxies will still be there tomorrow, still spinning, still waiting to be discovered, still growing with every pair of eyes that looks up in wonder. And you'll still be stardust, still part of the cosmic dance, still meaningful in ways you might never fully grasp. Sleep well, fellow traveler. The universe is vast, and you are home. The weight of knowing. There's something profound about living in this particular moment of cosmic history. We know enough to understand how vast the universe is, how ancient, how filled with galaxies beyond counting. But we don't know everything, not even close. That balance between knowledge and mystery is precious. It means we can appreciate the scale of things without losing the sense of wonder. Imagine if we knew everything, if every question had been answered, if the universe held no more secrets. Would we still look up at the night sky with the same feeling of awe? Probably not. It's the unknown that draws us forward, the darkness at the edge of our understanding that makes the light we've gathered feel meaningful. And right now, in your lifetime, humanity is poised at an extraordinary threshold. We have the technology to see farther than ever before. Webb is showing us galaxies from when the universe was barely 300 million years old. DESI, the Dark Energy Spectroscopic Instrument, has mapped over 14 million galaxies and quasars, creating the most detailed three-dimensional map of the cosmos ever made. These observations are revealing something intriguing, something that might change how we understand dark energy itself. For years, we assumed dark energy was constant, a fixed property of space that would remain unchanged forever. But new data suggests it might be evolving, changing over time. If that's true, if dark energy isn't constant, then the fate of the universe might be different than we thought. The expansion might not continue forever. It might, eventually, reverse. Some physicists now predict that in about 33 billion years, the universe could begin contracting, pulling back in on itself, ending not in cold, dark expansion, but in a big crunch. It's speculative, far from certain, but it's a reminder that even our best theories are still evolving, still being refined, still open to revision. The cosmic bubble we call home. There's another mystery emerging from recent observations, one that feels almost poetic in its implications. Scientists have discovered that our Milky Way, along with many neighboring galaxies, might be sitting inside a massive cosmic void, a billion light-year-wide bubble where space is less dense than average. This void could explain something called the Hubble tension, a puzzling disagreement about how fast the universe is expanding. Measurements of the nearby universe give one answer. Measurements of the distant universe give another. If we're inside this void, this underdense region, then matter around us would be pulled outward by gravity toward the denser regions beyond. That would make local space expand faster than average. It's as if we're living in a cosmic bubble, a quieter, emptier region surrounded by a richer, denser universe. And that bubble might have shaped our existence. Voids tend to be calmer, less chaotic. Fewer galaxy collisions, less intense radiation, more stable environments where life can take its time emerging. Maybe, just maybe, consciousness requires this kind of quiet pocket, a sheltered region where evolution can unfold without constant disruption. It's another way we're discovering that our location in space, just like our location in time, is remarkably fortunate. The sound of creation. When scientists talk about the cosmic microwave background, they're describing light, the afterglow of the Big Bang that fills all of space. But there's another way to think about it, as sound. In the first few 100,000 years after the Big Bang, the universe was so hot and dense that matter and energy were mixed together in a plasma. Sound waves, actual pressure waves, rippled through this primordial soup. When the universe cooled enough for atoms to form, those sound waves froze in place. They left an imprint, a pattern in how matter distributed itself across space. We can still see that pattern today, in the way galaxies cluster, in the slight preferences for certain distances between cosmic structures. Astronomers call them baryon acoustic oscillations, fossil sound waves from the universe's infancy. When you look at a map of galaxy distributions, when you see those subtle ripples in how matter is spread across billions of light years, you're seeing the echo of the Big Bang, the sound of creation itself, frozen in the structure of everything. It's beautiful when you think about it. The universe still carries the music of its birth, written not in sound waves anymore, but in the positions of galaxies, in the fabric of space-time itself. Jets that shape the void, even the emptiest regions of space, the great voids between galaxy clusters, turn out to be less empty than we thought. Recent observations have discovered massive jets of energy streaming from supermassive black holes in distant galaxies. Jets so powerful, they stretch for millions of light years, pumping electrons and atomic nuclei into the voids around them. These jets might be shaping the cosmic web itself, heating the voids, creating magnetic fields in regions we thought were essentially empty, enriching space with particles that will eventually become part of future galaxies. It's another reminder that the universe is never truly still, never truly empty. Even in the darkest voids, there's activity, energy, transformation. The cosmos is constantly recycling itself, matter flowing from galaxies into voids, voids being enriched and eventually collapsing to form new structures, everything connected, everything in motion. And you, lying there, drifting towards sleep, you're made of atoms that have been through this cycle many times, formed in stars, scattered into voids, collected into new clouds, formed into new stars and planets, and eventually, you. The privilege of this era. Your breathing is so slow now, so steady, your body heavy and warm, your mind floating gently between wakefulness and dreams. Perfect, just perfect. Let me remind you one more time how extraordinary this moment is, this era you're living in, this brief window of cosmic time. Humanity has existed for maybe 300,000 years, civilization for maybe 10,000, science, as we know it, for just a few hundred. And in that tiny sliver of time, we've gone from thinking Earth was the center of everything to knowing we're one planet among trillions, one galaxy among 2 trillion or more. We've discovered that the universe is expanding, that it had a beginning, that it's filled with dark matter and dark energy, that space itself can ripple and bend. We've built telescopes that can see galaxies as they were 13 billion years ago, detected gravitational waves from colliding black holes, measured the cosmic microwave background to incredible precision. All of this in just a few generations of human curiosity. You were born into this knowledge, into a time when the universe's story is being written in real time, when new discoveries happen regularly, when our understanding keeps expanding. That's rare, that's precious. For most of human history, people looked up at the same night sky and had no idea what they were seeing, no sense of scale, no understanding of time or distance or the vastness beyond. But you do, you know, and that knowing, that awareness, changes everything, letting the cosmos hold you. So as you drift now, as consciousness begins to fade, as sleep reaches up to pull you gently down, remember this. You're not falling asleep alone in a small room on a small planet. You're resting in the embrace of the cosmos itself. The atoms in your body are billions of years old. They've been part of stars, part of nebulae, part of other worlds, and now, for this brief moment, they're arranged as you. Tomorrow, they'll still be you, and years from now, decades from now, eventually they'll become something else, recycled again into the great cosmic dance. But tonight, right now, they're here, conscious, aware, able to think about 2 trillion galaxies and feel wonder. That's enough. That's everything. The universe doesn't need you to understand it completely. It doesn't need you to stay awake and solve its mysteries tonight. It just needs you to rest, to dream, to be part of its ongoing story. So close your eyes, let your jaw relax. Feel the weight of your body sinking into rest. The galaxies are still out there, still spinning, still shining, still growing with every pair of eyes that looks up in wonder. And you're still stardust, still meaningful, still home. Sleep well, traveler. The universe will be here when you wake. The music of the beginning. There's something almost magical about the cosmic microwave background when you understand what you're really looking at. It's not just ancient light, it's a recording, a preserved moment from when the universe was only 380,000 years old. Before that time, the universe was too hot for atoms to exist. It was a seething plasma, electrons and protons flying free, and light couldn't travel through it without being scattered. But then, the universe cooled just enough. Electrons and protons combined to form the first hydrogen atoms, and suddenly space became transparent. The light that had been trapped, scattered endlessly in that primordial fog, was suddenly free to travel. And it's been traveling ever since, for 13.8 billion years, stretched by the expansion of space from visible light into microwaves. When scientists map the cosmic microwave background, measuring tiny temperature differences across the sky, they're seeing something extraordinary. Sound waves, frozen in time. In those first 380,000 years, pressure waves rippled through the hot plasma, places where matter was slightly denser created, compressions like sound waves moving through air. When the universe became transparent, those waves stopped moving. They froze in place, leaving an imprint in how hot and cold the universe was at different locations. That pattern is still visible today, in the cosmic microwave background, in how galaxies cluster across space. You're seeing quite literally the echo of the Big Bang, the sound of creation itself, preserved in the structure of everything. The rhythm still plays, and here's what's beautiful about those ancient sound waves. They didn't just disappear. The pattern they created, those preferences for certain distances, still influences how galaxies form today. When you look at maps showing millions of galaxies, you can see subtle clustering, a slight tendency for galaxies to be separated by specific distances. That's the sound horizon, the distance sound waves could travel in the early universe before atoms formed and the music stopped. About 500 million light-years. That's the cosmic ruler written into space itself. And by measuring it, by seeing how big that distance appears from Earth, scientists can determine the geometry of the universe, whether space is flat, curved, infinite, or finite. It's like the universe is still humming with the song of its birth, a melody too deep for human ears, but visible in the arrangement of galaxies across billions of light years. The void around us. Your eyelids are so heavy now, aren't they? Good. Let them close. You can still hear me, still drift along with these thoughts. Remember that cosmic void we mentioned? That billion light-year bubble we might be living in? Scientists found it by listening to those sound waves, those baryon acoustic oscillations frozen in the cosmic microwave background. The sound, the pattern, looks slightly different depending on where you are, and from our perspective, from inside this potential void, the measurements suggest we're in a less dense region. It's like living in a quiet clearing in a vast forest. The forest continues beyond, denser, richer, but here there's space, room to breathe. Calm. And maybe that matters. Maybe consciousness needs these quiet pockets, these underdense regions, where stars form slowly, where galaxies don't collide as often, where evolution has time to create complexity. Maybe we're not just anywhere in the universe. Maybe we're in one of the special places, not because we're at the center, but because we're in a shelter, a cosmic harbor where life can emerge without constant disruption. The privilege of breath. Listen to your breathing for a moment. How slow it's become, how gentle. In and out, in and out, the rhythm of life, the rhythm of existence. That oxygen you're breathing, created in stars, fused from helium over billions of years, released into space when those stars died, gathered into clouds, formed into Earth, filtered through billions of years of photosynthesis, and now flowing through your lungs. Every breath connects you to stellar cores, to supernova, to the cosmic recycling that's been happening since the first galaxies formed. You're not just breathing air, you're breathing the universe, participating in the great exchange of matter and energy that's been flowing for 13.8 billion years. And as you breathe slower and slower, sinking deeper into rest, know that this too is part of the cosmic pattern, the rhythm of activity and stillness, energy and entropy, motion and rest. The universe itself pulses with this rhythm. Stars ignite and fade, galaxies form and merge, space expands and matter clusters, activity and quiet, forever. And you, for this brief moment, get to participate, to feel the rhythm, to rest within it. Drifting among the galaxies. Imagine yourself floating now, weightless, drifting upward through the atmosphere, past the clouds, through the thinning air, into the darkness of space. The Earth below you, so beautiful, so blue and alive, growing smaller as you rise. Past the moon, past the planets, out beyond the solar system where sunlight fades to just another star among billions. You're moving through the Milky Way now, stars all around you, some young and blue, others old and red, nebulae glowing in the distance, the spiral arms stretching in graceful curves. And then you drift beyond even that, beyond our galaxy. Looking back, you see the Milky Way as a whole, a spiral of light turning slowly in the dark. Around you, more galaxies appear. Andromeda, the Magellanic Clouds, thousands more, the Local Group, all bound together by gravity, drifting through space on their own cosmic journey. And as you float outward, farther and farther, more galaxies fill your vision. Millions, billions, 2 trillion and counting, each one a spiral of light, each one containing billions of stars, each one a universe unto itself. The cosmic web becomes visible, filaments of galaxies, clusters and superclusters, vast voids between them, the pattern of creation stretching in all directions. And you, tiny, insignificant, and yet aware, conscious, able to see and understand and feel wonder. The universe experiencing itself through you, looking at itself, knowing itself, for this brief, beautiful moment. When you look at the universe on its very largest scales, a pattern begins to appear. It's not the kind of pattern that's visible to the naked eye standing beneath the stars, or even one that could ever be seen from any single point in space. It emerges only through patient, methodical mapping, through the long, careful work of counting galaxies, measuring their positions precisely, and connecting the dots across billions upon billions of light years. When you step back far enough in perspective, something remarkable happens. The galaxies stop appearing as isolated points scattered randomly through space, and start forming structures that are immense and deeply interconnected. This is what we call the cosmic web, the grand architecture of the universe itself, a vast network of filaments and clusters and voids, stretching in every direction as far as light can reach and instruments can detect. The name web isn't poetic exaggeration or metaphor. It's actually quite descriptive of what we observe. Galaxies are not distributed evenly across the cosmos like stars on a flag. Instead, they gather along threads of matter that weave together into nodes, forming enormous clusters where many galaxies reside close together. These clusters are connected by filaments that can span hundreds of millions of light years, thin bridges of galaxies and gas stretching across the void. Between these filaments lie enormous voids, regions of space that are almost completely empty, vast expanses where there are few, if any, galaxies at all, just darkness and distance. The result is a pattern that looks in computer simulations like a three-dimensional web glowing softly against the dark. If you could somehow see it in its entirety, from outside, it would resemble a neural network or the branching of veins in a leaf, or perhaps even the filaments of electrical activity inside a living brain. The similarity is striking, almost unsettling. This web is not made of galaxies alone, though. The luminous parts we can see, the stars, the glowing gas, the bright clusters, are only the visible traces of something much deeper, much more fundamental. Beneath them lies the invisible scaffolding of dark matter. It's this hidden substance, making up most of the matter in the universe, that shapes the web's structure. Gravity pulls the dark matter into these filaments first, and ordinary matter simply follows along, drawn into the same paths by gravitational attraction. Where the filaments intersect, where multiple threads come together, the pull of gravity is strongest, and there, galaxies and clusters form naturally. Light, in other words, follows the dark. The universe builds itself along these invisible lines, tracing out a geometry set by forces we can't see directly, only infer through their effects. The cosmic web is the product of billions upon billions of years of evolution. In the very beginning, shortly after the Big Bang, the universe was almost perfectly smooth. A faint, even glow of matter and radiation spread uniformly in all directions. But even then, even in that nearly perfect smoothness, there were tiny fluctuations, infinitesimally small differences in density from place to place. Those differences, no larger than 1 part in 100,000, grew over time under the relentless influence of gravity. Denser regions, even slightly denser, attracted more matter, becoming denser still. Meanwhile, emptier regions grew emptier, as their matter was pulled away. Over billions of years, those small variations stretched and amplified dramatically, forming the first filaments, the first clusters, the first galaxies. The web we see today is the direct result of that slow amplification, the fingerprint of gravity acting on the primordial universe, preserved across cosmic time. When cosmologists simulate the formation of the universe on supercomputers, they start with a field of random fluctuations based on observations and let gravity do its work according to known physics. The results are astonishingly, almost eerily accurate. The simulations produce filaments and voids that match precisely what we observe in the real universe. The distribution of galaxies, their clustering patterns, even their motions through space, all fit the predicted pattern. The same structure appears across different scales, from small galaxy groups just a few million light-years across, to vast superclusters spanning hundreds of millions. This self-similarity, known as a fractal-like property, gives the universe a coherence that transcends any single scale. The pattern repeats, not exactly, but rhythmically, like variations on a musical theme. It's as if the cosmos were built from the same blueprint applied at different magnifications. The filaments themselves are truly colossal in scale. Some stretch for hundreds of millions of light-years, containing thousands upon thousands of galaxies strung like luminous beads on an invisible thread. The largest known structures in the universe, such as the Hercules Corona Borealis Great Wall, extend over 10 billion light-years, nearly a tenth of the entire observable cosmos. It's almost incomprehensible to imagine something that large, something that vast and continuous. And yet, when we map it carefully, the structure becomes clear. The galaxies are not randomly scattered as they might appear at first glance. They belong to this pattern, connected by forces that operate over distances that dwarf anything in human experience. Between the filaments lie the voids, vast, dark regions where very little exists. These voids are not truly empty in an absolute sense, but their density is far, far lower than average. They make up most of the volume of the universe, paradoxically, while the filaments and clusters contain most of its mass. If you could somehow drift into the heart of one of these voids, you would find yourself in a region of space where galaxies are distant and rare, where the nearest cluster might lie hundreds of millions of light years away in any direction. The darkness there would be almost perfect, almost absolute. The night sky would be nearly black, with only the faintest, most distant glimmers. Yet even in these emptiest places, faint traces of matter remain, a thin gas of hydrogen and helium, a few drifting galaxies lost in the vastness, perhaps invisible threads of dark matter passing through unseen. The web is continuous, connected, even where it looks like nothing at all. The cosmic web is more than just a static pattern of matter frozen in space. It's a living record of how the universe has evolved over time. The filaments trace the flow of material from the early universe to the present day. Galaxies move along them like traffic on cosmic highways, drawn ever toward the clusters at their intersections. Over billions of years, the web slowly changes shape. Filaments merge together, clusters grow more massive as they consume smaller groups. Voids expand as space itself stretches. Gravity continues to sculpt the pattern, pulling matter together wherever it can. But at the same time, the expansion of the universe stretches everything apart. There's a delicate balance between these two opposing forces, gravity pulling inward, cosmic expansion pulling outward. The web exists in that balance, frozen in slow motion, evolving gradually but never collapsing completely. It's a dynamic equilibrium, a cosmic dance that's been going on for nearly 14 billion years. It's easy to think of the universe as static when you look up at the night sky. The stars seem fixed in their constellations, unchanging from night to night and year to year. But on cosmic timescales, everything moves. The galaxies are drifting along the filaments like leaves carried on a vast, slow river. Clusters merge in slow-motion collisions that take hundreds of millions of years, sending massive shockwaves through the intergalactic gas, heating it to millions of degrees. Over tens of billions of years in the future, the web itself will stretch further and further as dark energy continues to drive the acceleration of cosmic expansion. The filaments will thin, growing fainter. Eventually, distant galaxies will slip beyond our cosmic horizon one by one. Their light will be redshifted so much that it fades from view entirely, disappearing into the background. The cosmic web will remain, but our part of it will grow lonelier, more isolated, as the universe ages around us. To truly understand this immense structure, astronomers use vast galaxy surveys, enormous projects that map millions of galaxies in 3 dimensions, recording not just their positions on the sky, but their distances from us. One of the most famous is the Sloan Digital Sky Survey, which has created detailed maps of the universe spanning billions of light years. When you plot all that data, when you visualize it properly, the pattern leaps into view immediately. Dense knots where clusters form, long, thin filaments connecting them, and dark voids between, empty and silent. The structure is unmistakable once you see it. The web looks almost alive, like something organic that grew rather than something that was assembled. It's a frozen moment of motion, a snapshot of a process that's still unfolding. The filaments are not empty lines drawn through space. They're filled with gas and dark matter, the raw material for future generations of galaxies yet to form. Observations using X-ray telescopes and radio telescopes have begun to detect the faint glow of this intergalactic medium, heated to extreme temperatures by shock waves as galaxies and clusters interact. The temperature of this gas can reach millions of degrees, though its density is incredibly low, just a few atoms per cubic meter, thinner than the best vacuum we can create on Earth. Yet it's there, connecting everything. It's the universe's connective tissue, thin and nearly invisible, but absolutely essential. Without it, Galaxies would be isolated islands floating in darkness, separate and alone. But with it, they're part of a grand continuum, exchanging matter and energy across scales we can hardly imagine. Our own galaxy, the Milky Way, sits within this vast web. We're not at the center, but we're not at the edge either. We're part of a larger structure called the Laniakea supercluster. The name comes from Hawaiian and means immense heaven. It's a fitting name. Laniakea encompasses over 100,000 galaxies, stretching 500 million light-years across. Within it, the Milky Way belongs to a smaller group called the Local Group, which includes Andromeda and a few dozen smaller companion galaxies. These, in turn, are connected to the Virgo cluster and other nearby clusters, all bound together by gravity into one continuous flowing structure. The cosmic web, when seen this way, is not just an abstract map of distant space. It's our address in the universe. It's where we live, cosmically speaking. Understanding the detailed shape of this web is one of the central goals of modern cosmology. It tells us not only how the universe is arranged right now, but how it came to be this way. The size and distribution of the filaments depend directly on the amount of dark matter, the properties of dark energy, and the physics that govern the very early universe just after the Big Bang. By studying the web's geometry carefully, we can test our theories of cosmological evolution. We can measure how fast the universe expands, how structures grow over time, and even how the invisible components of reality, dark matter and dark energy, behave under different conditions. The web is not just a beautiful pattern, it's a key that unlocks answers to fundamental questions about the universe's past, present, and future. The way the web looks today reflects billions of years of competition between gravity and expansion. Early in the universe's history, matter dominated everything. Gravity pulled everything inward, forming structures rapidly, efficiently. But as time went on, dark energy began to exert more influence on the cosmic balance. The expansion accelerated. The growth of new structures slowed down, then nearly stopped. The web we see now is the result of that long tension, that cosmic tug-of-war, dense regions growing denser, while the spaces between them stretch wider and wider. It's a dynamic equilibrium, always shifting but always following the same fundamental rules written into the fabric of space-time itself. To see the web as it truly is, in all its complexity, we have to combine data from many different sources. Optical surveys show us the positions of galaxies as points of light. Radio and X-ray observations reveal the hot gas that fills the space between galaxies, glowing faintly in the darkness. Gravitational lensing, the bending of light by massive objects, maps the invisible dark matter that holds it all together. Together, all these observations form a composite picture, one that's still incomplete, still being refined, but growing sharper and more detailed every year. Supercomputers run massive simulations, tracing how the web might look billions of years in the future as the universe continues to expand and age. The agreement between simulation and observation is remarkable, almost miraculous. It tells us that despite all our uncertainty, despite all we don't yet know, we've captured something essential about how the universe builds itself. When you think deeply about the cosmic web, it's natural to wonder, why does it look this particular way? Why this pattern and not another? The answer lies in the fundamental physics of gravity and motion. Small fluctuations grow inevitably into large structures because gravity acts universally, everywhere at once, pulling matter together, wherever it's even slightly denser than average. The same process repeats across every scale, creating a self-organizing pattern that's neither completely random nor perfectly regular. It's the natural, inevitable outcome of simple physical laws applied over vast distances and unimaginable stretches of time. The result is a universe that looks both chaotic and ordered, a complexity born from elegant simplicity. There's something quietly humbling in the realization that the universe's largest structures mirror shapes we find in nature on much smaller scales. The branching of trees reaching towards sunlight, the veins in a leaf carrying nutrients, the neurons in a brain forming connections, all of these follow similar mathematical principles, the same underlying logic. Patterns of connectivity, efficiency and balance recur across different magnitudes of scale. The cosmos, in its immense enormity, seems to echo the same logic that governs life here on Earth. It's not that one directly causes the other, but that both arise from the same underlying mathematics of growth, connection, and optimization. The web of galaxies and the web of neurons in your brain are cousins in form, different in content and scale, but similar in essential structure. And though we can never step back far enough to see the whole structure with our own eyes, the maps we've painstakingly built give us a sense of it. The cosmic web is not a single object existing in one place. It's a pattern that exists everywhere at once, woven through the entire universe like a hidden fabric underlying reality itself. You are part of it, connected to it. The atoms in your body trace their ultimate origin back to stars that formed along its filaments billions of years ago. The gravity that holds your feet firmly to the ground is the very same gravity that shaped its elegant, sweeping curves. The web is not out there, somewhere distant. It's the fundamental structure of everything that exists, including you. As we continue to study it with ever more sophisticated instruments, the web will keep revealing new details, new layers of complexity. We'll measure its temperature more precisely, map its density variations, detect its subtle vibrations as structures form and merge. We'll track how galaxies move along its threads, how clusters grow at its intersections. We'll learn how the invisible dark matter flows, silently guiding the visible light we can see. And each new discovery will remind us of a profound truth, that the universe is not a collection of separate, disconnected things floating in empty space. It's a connected whole, a unified structure. The filaments are the physical manifestation of that connection, the threads that literally tie existence together across unimaginable distances. The shape of the cosmic web is, in the end, a direct reflection of the universe's deepest nature, structured yet open, vast yet cohesive, always evolving, always changing. It's a constant reminder that what seems empty is actually full of invisible structure, that what seems separate is actually joined in ways we're only beginning to understand, that the darkness between galaxies is not mere absence, but structure itself, invisible scaffolding, holding everything in place. The web stretches through everything we can see and far beyond, unseen but undeniable, binding light to dark, matter to energy, gravity to space, and us to the rest of the cosmos. We're part of the pattern, woven into the fabric, and that connection, that belonging, is perhaps the most profound discovery of all. The night sky looks eternal, doesn't it? The stars, the galaxies, those faint clouds of light stretching across the darkness. They seem so fixed, so endless, so completely beyond the touch of time. But here's the truth. Nothing in the universe lasts forever, not even the light that fills it. Every star that burns so brightly, every galaxy that shines across the void, is moving slowly, inevitably toward an end. Some will fade quietly, gently dimming like candles in the wind. Others will end in brilliant bursts of light, spectacular supernovae that briefly outshine entire galaxies. Over long enough timescales that dwarf all of human history, even the universe itself will grow dim. It's not a tragedy, though it might sound like one at first. It's simply the way things change when time is given endless room to stretch beyond all imagination. The universe has a beginning, and someday, in the unimaginably distant future, it will have an ending. Not a sudden one, not a dramatic collapse, just a gradual dimming, a slow, peaceful descent into quiet stillness, a gentle fading into night. When you look up at the Milky Way on a perfectly clear night, far from city lights, you're seeing a moment frozen in cosmic time. The stars are still forming in those glowing nebulae. The spiral arms are still bright with young, hot clusters, but that activity, that creative energy, is already slowing down. The vast clouds of gas that fuel the birth of new stars are being used up, gradually, little by little. Over billions upon billions of years, the rate of star formation in our galaxy will continue to decline. The brilliant blue stars that light up the spiral arms today will burn out relatively quickly, living fast and dying young. They'll leave behind only redder, cooler suns that glow more softly, more gently. Eventually, after enough time has passed, the night sky will begin to fade. Those last young stars will die one by one, and no new ones will replace them. The galaxy will still exist, certainly, but its light will thin noticeably. Its color will deepen to red and amber. Its edges will grow dim and harder to see. The same gradual fading will happen everywhere across the cosmos, in every galaxy, in every cluster. The end of light doesn't come all at once. You see, it unfolds in stages, each one lasting billions or even trillions of years. The first stage is the fading of the bright, short-lived stars. These massive suns, dozens of times heavier than our own sun, burn through their nuclear fuel incredibly quickly. They live fast, shining brilliantly for just a few million years before ending their lives in spectacular supernova explosions. Those explosions scatter newly forged elements into space, carbon, oxygen, iron, gold, seeding the raw material for the next generation of stars. For a while, this cycle continues, repeating again and again. Stars are born, live, die, and their ashes become new stars. But as the supply of fresh gas gradually runs out, that beautiful cycle slows down. Galaxies that were once filled with vibrant star-forming regions become quieter, more sedate. The bright spiral arms lose their sharp definition. The universe's color palette shifts subtly from brilliant blue and white to warmer yellow and red tones. The cosmos grows older in appearance, more mature. In the far, far future, perhaps 100 trillion years from now, an almost incomprehensible span of time, the very last stars will form. They'll be small, cool, and remarkably dim, red dwarf stars that burn their fuel so slowly, so efficiently, that they can live for trillions upon trillions of years. These faint suns will glow quietly, patiently, while the rest of the universe fades around them into darkness. When they eventually exhaust their hydrogen fuel, they'll become white dwarfs. These are incredibly hot, incredibly dense remnants, collapsed stellar cores that shine only with leftover residual heat. Slowly, over time periods we can barely conceptualize, even that heat will dissipate into the expanding void. The white dwarfs will cool gradually into black dwarfs, cold, dark, invisible spheres drifting silently through space. The galaxies will still exist in some form, but they'll be completely invisible. No light, no heat, nothing to mark their presence. The universe will have entered what physicists call the degenerate era, a time when all remaining light comes only from the slow, inevitable decay of dying matter. Before that unimaginably distant age arrives, though, there will be a long, long period of transformation and change. Galaxies will continue to collide and merge with one another, their stars pulled and stretched into new arrangements by gravity. Our own Milky Way and the Andromeda Galaxy, for example, are already on a collision course. They'll merge in about 4 billion years from now. But the collision won't be violent in the way you might imagine. The stars themselves are so incredibly far apart that very few will ever collide directly. Instead, the two galaxies will pass through each other like ghosts, their overall shapes distorted and transformed by mutual gravity. Their massive gas clouds will compress where they meet, triggering one final burst of intense star formation. Over time, measured in hundreds of millions of years, the two spirals will merge completely into a single, larger elliptical galaxy. Quieter, redder, older. This process isn't unique to us. It's happening everywhere across the universe. The cosmos is constantly slowly reshaping itself even as its overall light gradually declines. On an even larger scale, the clusters and filaments of the cosmic web will continue their slow evolution. Gravity will keep pulling galaxies together into ever larger structures, while at the same time, dark energy, that mysterious force driving the acceleration of cosmic expansion, pushes them apart. Eventually, inevitably, dark energy will win the long struggle. The expansion will finally outpace gravity's ability to bind new structures together. The cosmic web will thin and stretch. Galaxy clusters will grow isolated, drifting slowly away from one another. The observable universe will become a patchwork of island galaxies, each one surrounded by deepening darkness, its nearest neighbors receding steadily beyond the horizon of visibility. The universe will appear to empty itself, though nothing has truly vanished. The light will still exist, but it will be stretched by expansion, redshifted into wavelengths so incredibly long they'll fade completely beyond any possibility of detection. At that distant point, the night sky visible to any surviving civilization would look profoundly different from what we see now. The great galaxies that fill our telescopes and inspire our wonder would no longer be visible at all. The cosmic microwave background, that faint afterglow of the Big Bang itself, would have stretched so much that it too would become undetectable. To those distant observers, if any exist, the universe would seem static, cold, and nearly empty. All the evidence of its own dramatic beginning would have vanished beyond reach, erased by time and distance. For them, cosmology as we know and practice it would be effectively impossible. The story of expansion, of countless galaxies, of light itself would all be hidden in the unreachable past, like a memory completely erased by the passage of unimaginable time. But even then, even in that cold and lonely future, the universe wouldn't truly be over. It would simply be changing phase, transforming into something different. The remaining stars would continue their slow evolution, one by one. Black holes would dominate the centers of galaxies, slowly swallowing what remains of gas and dust and unlucky stars. Some black holes might even merge, forming larger and larger cosmic giants. These massive objects would be among the last luminous things in the far future, shining faintly in X-rays as they consume the occasional stray matter that drifts too close. Around them, the remnants of long-dead stars, white dwarfs, neutron stars, and lonely planets would orbit in perfect silence. Eventually, even those ancient orbits might decay as gravitational interactions and black hole mergers slowly rearrange what little remains. Over time, scales that truly defy imagination, even the black holes themselves will begin to fade. According to quantum physics, they're not perfectly black after all. They emit an incredibly faint radiation, now known as Hawking radiation, caused by quantum effects right at the edge of the event horizon. This radiation is unbelievably weak, completely undetectable for black holes of ordinary size, but over trillions upon trillions of those years, it slowly adds up. Very gradually, black holes will lose mass, bit by microscopic bit. They'll shrink over eons. Eventually, after a time so vast that numbers become meaningless, they'll evaporate entirely. The largest supermassive black holes, those millions or even billions of times the mass of our Sun, will be the absolute last to go. Their final photons will be released after a period of time so incomprehensibly long, it defies any attempt at description. After that, there will be no stars left, no galaxies, no light, only cold, scattered particles drifting endlessly through an ever-expanding void. This is what physicists call the heat death of the universe, a time when energy is perfectly, completely, evenly distributed, when no more work can be done anywhere, when everything that could possibly happen has already happened. It sounds bleak, doesn't it? But it's not really an ending in the truest sense. It's a state of rest, a perfect balance reached after endless ages of transformation. The same physics that gave rise to stars and galaxies, and perhaps even life, will eventually bring everything to equilibrium. Entropy increases, as it always has, as it always must. The lights go out slowly, but the universe itself remains, continues, persists in a new form. It's strange and somewhat melancholy to imagine such a future, when everything familiar has faded away completely. Yet even now, we're living in a universe that's already well past its youth. The first stars formed more than 13 billion years ago. The peak of cosmic star formation happened roughly 10 billion years ago. Since then, the rate has been steadily, gradually declining. The cosmos is no longer young, but it's still wonderfully, brilliantly full of light, and it will remain so for billions of years to come. The galaxies still glow beautifully, the stars still shine brightly, and the night sky, for all its quiet mystery, is still vibrantly alive with light and possibility. We exist in what we might call a luminous age, a brief but precious window of cosmic brilliance, sandwiched between the universe's hot, violent beginning and its cold, quiet future. Some scientists have wondered whether that distant future might yet hold surprises we can't anticipate. Perhaps dark energy will change its properties over time, fundamentally altering the universe's ultimate fate. Perhaps new physics will emerge from the quantum foam, allowing new structures to form even after all the stars have faded. There are even theories suggesting that quantum fluctuations could potentially create new universes, tiny bubbles of space-time that expand to become entire cosmoses of their own. In that sense, the death of this universe might actually be the birth of countless others. The lights go out here, but they might flicker on elsewhere, in realms we can't yet imagine. The cosmos could be an endless, eternal cycle of creation and dissolution, each universe somehow seeding the next. Still, from where we stand right now, looking up at the stars, the idea of approaching darkness is powerful and meaningful. Light has always been our primary way of knowing, of understanding. The galaxies we observe, the stars we navigate by, all the data we carefully collect, all of it fundamentally depends on light in one form or another. When we try to imagine a universe without light, we're imagining a universe without witnesses, without observers, but that's only our limited perspective as light-dependent beings. The universe doesn't actually need light to exist. It simply is. The end of shining things doesn't mean the end of being, of existence itself. It just means a profound change in what being looks like, what form it takes. Even in that incredibly distant future, when the last lonely photons fade into the background radiation, something of light will remain. The information carried by every particle, every interaction, every wave that ever existed, all of it will still be there in some form, dispersed but never truly destroyed. The universe will have written its entire story, encoded in the final distribution of energy and matter throughout space. And while no conscious being may be there to read that story, it will still exist, permanently imprinted in the fabric of space-time itself. The lights will go out, yes, but the memory of light will never vanish completely. It's profoundly difficult to think about such vast timescales, trillions upon trillions of years, numbers so staggeringly large they completely outstrip human imagination, breaking our ability to comprehend. But perhaps that's exactly the point of this contemplation. The universe invites us to stretch our sense of time itself, to see existence not as something brief and fleeting, but as something continuous, eternal, ongoing. Our own individual lives are short flashes of awareness, brief sparks in the darkness, but they happen within a story that literally spans eternity. When we look up at the stars tonight, we're witnessing the middle chapter of that vast story, the luminous part, the bright and beautiful moment when the universe is at its absolute peak brilliance. We're part of the light before it fades, and there's a quiet, profound comfort in knowing that, understanding it deeply, the same fundamental processes that will one day dim the stars also made them shine brilliantly in the first place. The same physics that will eventually cool the galaxies into darkness also built them, forged them, gave them form and structure. The universe isn't moving toward an ending in any moral or tragic sense. It's simply completing a natural cycle, following the laws that have always governed it. The heat will fade over unimaginable time, but the balance, the equilibrium will hold. The cosmos will finally rest. When the lights go out at last, the night will not be truly empty. It will be full of the traces of everything that ever was. The atoms forged in the hearts of stars, the gravity that shaped galaxies into spirals and ellipticals, the photons that once illuminated the darkness, bringing knowledge to those who looked up and wondered. Even in silence, even in cold stillness, those traces will endure. The universe doesn't vanish when it grows quiet. It simply changes form, transforms into something new, and perhaps somewhere in that infinite quiet, the seeds of new light will gather again somehow, waiting patiently for another beginning, another cosmic dawn. The lights go out slowly, so incredibly slowly, that no single generation, no civilization will ever notice it happening in real time. The stars will keep burning steadily. The galaxies will keep turning gracefully, and life in whatever forms it might take across the cosmos will go on for countless eons. But the direction, the trajectory, is clear and unchangeable. The universe is cooling, expanding, settling gradually into stillness. The same way a fire burns bright and hot before slowly fading to glowing embers, the cosmos blazes brilliantly now before its long rest. And we, for one brief and precious moment, are here to witness it happening. Beings made of starlight, watching light itself shine and dance across the darkness. If you could somehow stand outside of time entirely and watch it all unfold, from the very first stars igniting to the last one flickering out, you would see the universe like a single breath. A rise, a pause, a slow, gentle exhale into stillness. It would begin in a spectacular flash of light and energy, and end in profound calm. And somewhere within that cosmic breath, we would appear. We'd look up with wondering eyes, we'd see the glow all around us, and we'd marvel at what it all means. The lights would shine brilliantly for us, and then, long after we're gone, they would keep shining for others, whoever they might be, until finally, inevitably, they fade. But even that fading carries its own kind of beauty, its own meaning. The universe's long twilight isn't a failure or a cosmic tragedy. It's the natural, inevitable outcome of energy finding its final balance, of time doing what it does best, moving steadily forward. The lights will go out, yes, but before they do, they will have illuminated absolutely everything. The galaxies, the planets, the atoms, the molecules, and the minds capable of knowing them, of understanding them, of appreciating them. And that illumination, that brief moment of cosmic awareness, will have been enough, more than enough. It will have been everything. It's hard to imagine something as vast and incomprehensible as the entire universe fitting inside something as small and fragile as a human thought, isn't it? Yet in a very real way, it does. Everything we know about galaxies, about stars, about the nature of time and space itself, exists as intricate patterns of understanding inside our minds. The universe, with all its impossible scale and ancient age and infinite complexity, is far too large to experience directly. We can't walk across it on foot. We can't stand outside it to see its true shape from a distance. All we can really do is think about it, hold it in our awareness carefully, in fragments of light and logic, like a delicate reflection shimmering in a perfectly still pool of water. It's strange and wonderful to realize that this infinite thing, this structure containing uncountable galaxies, can be contemplated, imagined, understood by a brain that fits comfortably inside a human skull. It's even stranger when you consider that the universe itself built the very minds that now turn inward to imagine it. Every single atom in your body was forged in the heart of ancient stars. The iron flowing through your blood right now came from a supernova explosion billions of years ago. The calcium in your bones, giving them strength and structure, came from stellar furnaces that burned before Earth even existed. The carbon that forms the backbone of every molecule in your cells, the oxygen you breathe, all of it came from long-dead suns that lived their lives and died, scattering their remains across space. When you look up at the night sky, you're looking directly at the source of yourself, the galaxies out there, so distant they seem completely separate and not distant in kind. They're only distant in space, in physical separation, but not in nature, not in essence. You're made of exactly the same materials, just arranged differently, following the same fundamental laws. You're a small, localized expression of a vast, universal pattern. The universe doesn't just surround you like a backdrop. It continues through you. You are the universe, in a very literal sense. It's easy to forget this profound connection, because we naturally live on human scales. Our lives unfold in years, counted on calendars, our days measured in hours, our movements across distances we can walk in minutes. The universe, meanwhile, moves in billions of years, across distances so vast that light itself takes eons to cross them. The enormous mismatch between those scales can make it feel like we live in a completely separate world, one of human time and ordinary daily experience, somehow apart from the grand cosmic one. But they're not separate at all, not even slightly. The small faithfully reflects the large. The curvature of a simple teacup follows exactly the same geometry that governs the orbits of planets around stars. The steam rising gently from its surface follows the same thermodynamic laws that drive the motion of entire galaxies through space. The entire cosmos is encoded, written, preserved in the small details of the world immediately around you. If you know how to look, if you train yourself to see the connections, the universe reveals itself everywhere. When you pour tea and watch the surface ripple outward in concentric circles, you're watching gravity and fluid motion at work. The way the liquid settles gradually into stillness perfectly mirrors the way matter finds equilibrium in the vastness of space. The swirl of steam rising above it echoes the turbulence of massive gas clouds forming new stars, light years across. The warmth that slowly fades into the surrounding air demonstrates the same principle that drives entropy throughout the entire universe. Energy spreading evenly, inexorably seeking balance, moving from hot to cold. These parallels aren't just poetic metaphors or pretty analogies. They're real, physical continuities. The same laws of physics govern both situations completely. They're just scaled differently by size and time. A cup of tea cools in minutes. A galaxy cools over billions of years. But the underlying principle remains absolutely the same. This is why scientists often say that to truly understand the universe, you don't always have to look outward through telescopes. Sometimes it's enough to simply look closely at what's right in front of you. The universe isn't only a place, a location somewhere out there. It's a set of laws, of relationships, of mathematical patterns that repeat endlessly across every scale imaginable. When you hold any object in your hand, you're holding the product of those same cosmic relationships. Atoms arranged according to the rules of electromagnetism, molecules bound together by the exchange of energy. matter organized by forces that have operated continuously since the first seconds after the Big Bang. The universe is not distant and unreachable. It's intimate. It's in your hands right now, in your breath, in every heartbeat that depends ultimately on energy from starlight, filtered through billions of years of time. That realization fundamentally changes what it means to study the cosmos. It's not about separating ourselves from it, not about gazing from a safe distance as detached observers. It's about recognizing that the very act of observing is itself part of the system we're studying. When we point a telescope toward a distant galaxy, we are quite literally the universe looking back at itself, becoming aware of itself. The light that enters the telescope lens began its journey in the nuclear heart of a star billions of years ago. It traveled across expanding space for eons, and it ended its long journey inside a human-built instrument, constructed by beings who themselves evolved from that same cosmic material. The circle completes itself perfectly. The observer and the observed are made of exactly the same thing, following the same rules. When you think of it that way, the phrase "a universe in a teacup" doesn't sound like exaggeration or flowery language at all. It's a simple reminder that the cosmos is not something impossibly far away and unreachable. It's right here, condensed into the familiar, the everyday, the ordinary. Every small detail of existence holds within it the fundamental rules of the whole. The ripples in your morning drink, the gentle glow of a candle flame, the movement of air through an open window, all are governed by the same laws that shape galaxies into spirals and stars into spheres. The scale changes dramatically, but the underlying truth does not. The universe is fractal in its logic, repeating itself in different sizes, different forms, but always with the same beautiful underlying order. There's something deeply calming about understanding this. The vastness that once felt intimidating, overwhelming, becomes close, almost domestic, familiar. The same universe that stretches across billions of light years is also the one that allows you to exist at all, that makes your existence possible. The cosmic and the personal are not two separate realities running parallel. They are one continuous story, one unified narrative, unfolding simultaneously at different magnitudes of scale. When you breathe, you're participating in cosmic chemistry. When you think, form thoughts and memories, you're engaging in the organization of matter into consciousness. One of the universe's most remarkable achievements. The universe expresses itself in vast galaxies, yes, but it also expresses itself just as truly in you, in every person, in every living thing. The idea that the entire cosmos lives within awareness isn't merely a poetic claim or mystical thinking. It's a literal, physical truth. The information of the universe, the structure of its laws, the shape of its history, is stored and represented in biological brains as specific patterns of electrical and chemical activity. When you close your eyes and imagine the Milky Way, or recall an image from the Hubble Deep Field that you saw once, that image exists as neurons firing in specific sequences throughout your brain, creating a detailed model of the cosmos within your mind. You are, in a very literal sense, holding galaxies inside your head, not their physical matter, obviously, but their meaning, their essence, their information. The same light that traveled billions of years to reach Earth is converted through your eyes into neural signals, into thought, into memory, into understanding. The universe becomes self-aware through exactly that process, through you, through every conscious mind that has ever wondered about the stars. The lights shine in the darkness, and somewhere, someone looks up and sees them, and in that moment of seeing, of witnessing, the universe knows itself, contemplates itself, marvels at its own existence. And that might be the most beautiful thing of all.